So this is example 2.1, which I want to do the same thing. By the way, I made a mistake here, which not a mistake, but I forgot to add something. So I'm going to go and I'm going to add this right now. We just plotted position versus time here, but we didn't plot velocity. So we should plant velocity right here. Now remember, all of these velocities are constant. I should say here is that I forgot to plot velocity versus time. Now note, all of these are going to be straight lines. Why are they going to be straight lines? Because we're talking about constant velocity. So when I look at my curve here, let's look at this guy right here. Let's say that this is my velocity curve. So the first thing that we want to do here is that if I look at the red, we could see here is that the red line has a smaller slope as it goes from point 1 to point 2. So I'm going to come in here and I'm going to say that this is 1 and then this point is 2. That means here, because this is a positive quantity, this v is small and it's positive. That's not true of the green line, right? You can see that the green line is very steep. So if I look at this here, and it's negative, so I have to show that negative somewhere. So here I go. So then over here, I'm going to come and I'm going to look at this guy, and I'm going to go to point 4 right here. And one of the things that you see here is that look at the magnitude of the value. This tells me that this is large, right? This has a large value because you could see here that the height here, that's small, but this height here is definitely farther from the origin, so therefore it has to be like that. Second of all, this is negative. So even though it's large, this value here is negative. That's how I write velocity, right? It has a magnitude and it has a direction. So the direction in this case, this tells me, if I look at this, that this guy is really minus v. That's my vector right there. In this case here, my vector here tells me that this is plus v. I get 2 pieces of information from that. Now let's do the following thing here. So I want to sketch the position and velocity graphs for the following motions. Okay? Just exactly what we did before. Okay, so let's start with A. So A says Carmen walks to the bus stop, waits for the bus, and then rides to campus. Assume that all the motions are along a straight line. So here we go. So we assume only constant velocities here. So we got to be careful here. I do not want to include change in velocity. It turns out to add change in velocity is not a challenging thing to do. But to get the picture right becomes important. So what we'll say here is that all velocities, let me bring this over here, all velocities are constant. So this means we do not account for changes in velocity right now. And all we're trying to do here is that we're trying to make things easy. Okay, just easy. So let's start with the motion diagram. Carmen walks to the bus stop. So here's the way I look at it. So if I look at the motion diagram, of Carmen, what do I see? Well, she starts off at this point 0. And we know that she's walking. Because she's walking, she is moving at constant velocity. But look what happens here. So she's moving from here to here, here to here, here to here. And then what she's going to do here is that she's going to stop instantly, right? So this point right here, we can see here that this velocity is this big, and we're moving at constant velocity in this interval here, right? This is constant velocity right here. But then I'm going to say something is super non-physical. Carmen instantly stops. She changes her velocity like infinitely fast. And at that point, she then stops and waits for the bus. So she instantly stops here. So that means here that what we're saying here is that she is waiting for the bus with v equal to 0. Is that a realistic picture? Of course it's not. But now let's look at a second stage. Now she gets on the bus. And I think what I'm going to do here is that I'm going to copy this and try to put two pictures together here. So now she's been waiting for some time here, right? Here she is, she's waiting. And so now what happens here, after some time, at the same point, she's waiting and getting on the bus. Now this picture is going to be crazy because guess what? The bus doesn't stop. The bus continues to move. So what does Carmen have to do? She has to jump onto the moving bus. How realistic is that? Not at all. But this is to make things as easy as possible. I didn't say this would be a realistic problem. So now what happens next? She is moving at constant velocity again, right? She is now going to move at constant velocity again because she's on the bus. So now that she's on the bus, she jumps on the moving bus and she continues to move at a higher speed. So when we look at this, she is moving faster right there. I don't even need to have these dots right here. They're both constant intervals. So now the question, how do we draw this picture? Because there's an interval that talks about waiting. So here I go. So now let's plot this motion using position versus time and velocity versus time. So what I have a tendency to do is to draw two coordinate systems for position and velocity right on top of each other. So here I go. So I'm going to go something like this. Going to look like this. And then this other one, I'm going to draw right below it. And it's going to look like that. So this is going to be position, velocity, time, and time. So here we go. So what's going to happen here? Carmen is walking. Look at the motion diagram, right? Maybe we can bring this down here, copy it, so that way we don't have to be going up and back. So she moves at a slower speed. So here we go. So we're going to say here is that her slope looks like this. And what you're seeing here is that this is the interval where she's moving at constant velocity. Now, if I look at my delta x, this is my delta x right there. Okay, so I'm looking at this curve, and you're seeing here that there's a slope to this. So we could then say that this is Carmen's velocity. And it had two pieces of information. It's moving at a speed of v, that's the slope, and it's moving to the right because it has a positive slope. And then what's going to happen next? She waits for a period of time. Look what happens. Note that in this case, this is where she's waiting. Note that delta x is equal to 0, which then immediately tells us that v is equal to 0. So I look at this next interval, and you could see that there's no change in position. That's my waiting right there. And then she catches the bus, and the bus moves faster. So in this case, let's say that the bus now moves like this here. And if you look at this section here, and you know, I should have been drawing these all the way down because they tell us about the intervals, which is really important. And you can see here that this is the piece that we have to focus on right here. And so in this situation, you could see that this is a bigger x. And so therefore, this guy is the bus's velocity. And in this case, you can see here is that this bus has a high velocity and it's moving to the right. So then the question, what's the velocities looking like? Well, we can see here is if I look at the slope is small. So what am I seeing? I'm seeing a really small slope right here. So this is my value of v. And then all of a sudden, when it's waiting here, you could see that the velocity drops to 0. And then it jumps to a higher speed. And you can see here is that it's going to jump all the way up here discontinually. And I'm going to get to this higher speed because this point is higher than this point right there. So you're seeing that these two are connected to the position curve. And that would be my motion diagram right there. Excuse me, not my motion, but my plot of the motion diagram. Okay, so now let's go look at this guy here. Let's look at this one other example. And this is B here. And it says, in B here, it says that the quarterback drops back 10 yards from the line of scrimmage and then throws a pass 20 yards to a receiver who catches it and sprints 20 yards to the goal. Draw your graph for the football. Okay. So let's look at these things here. So the first thing that I would look at is that I think I'm going to try to draw me a motion diagram so that I see what I'm looking at. Okay, so let me conceptualize this by starting with the motion diagram. So let's give these people some names here. How about if we start with, I don't know, quarterback Joe? So it says here that quarterback Joe drops, which really means moves backwards 10 yards. So I got to define an origin. So here I am. So once again, I am not, because we're graphing, I'm not considering changes in velocity yet. So I'm going to say that this point right here is going to be my origin right here. So this is my origin, which is, of course, x equal to 0. So if he drops back, as far as football is concerned, he's walking back slowly. He's not running back. So let's say here is that now I'm going in this direction to right here, let's say. So I'm just sort of like guessing here. I should have probably scaled this. So I'm going to say that if he walks back 10 yards, then this point right here, at this point, this is where that's the negative 10-yard mark. So Joe cannot stop instantaneously. He has to change his velocity. But we're in La La Land in saying that we're just going to allow these things to happen just so that we can get the graph right. Now he's going to throw the ball to a receiver. Let's say that the receiver's name Patty. So here we go. So at this point, at the 10 mark, he instantly stops and throws. So if I say stops and throws, we're assuming here that the ball has to be moving faster. So where is the receiver Patty at? Well, he throws the ball 20 yards. So that means I have to go 1, 2, 3. This is where receiver Patty catches the ball. So if I now start looking at my velocity vectors, I'm going to assume here is that it's going to go 1, 2, 3. Well, I got lucky here. So here's my dots. And then right here, what do we say? This is the plus 10-yard mark. And we say here is that the ball stops instantly. Is that possible? No. There has to be a change in velocity. Now it says that she catches and sprints 20 yards. So if she catches and sprints, if 3 squares is 10 yards, then this is going to be the 20 mark, and this would then be the 30-yard mark right there. So does the ball move the same speed? Does the receiver Patty move the same speed that the ball is thrown? No, she moves slower. So then I'm going to come in here and I'm going to say that her speed is now going to be slower. So if I look at this thing, I need to purposely draw smaller arrows because Patty can't run as fast as the ball is thrown. So now if I start putting in my values for my speeds here, I'm going to scale this so this looks something like this, so you could see that the orange is definitely larger than the blue, but that the speed of the ball thrown, that this has to be higher like that. So now let's go plot these. Okay, this will make it easier by doing this fake stuff to actually look at this. So here's my two graphs. So I'm going to go, there's my position. I might have to scale these, I don't know. Let me move this all the way over here just in case. And then here's my velocity right here. Okay, so here I go. Look at that motion diagram. That ball is going negative. So when I look at this thing, I'm expecting a slow speed. So I start here at the origin and I move backwards. So my position is going in the negative direction here. So right here, you're seeing that this is the ball moving back with the quarterback here. So this is effectively the quarterback's speed. So what's it going to be? It's going to be about this big, and it's going to be left. That's what that slope is telling me. Now the ball is thrown. And so for a short time, this ball moves very fast. So if this is minus 10 yards right here, this has to be plus 10 yards. So then when I look at my speeds here, I need to have a steep slope from there to there. So right here, we could now see that this is the thrown ball's speed. And how do we write this here? Well, that has a high speed and it's going to the right. And then the ball is moving faster than the blue, but not as fast as the orange here, as the runner. So let's say that this has to be less of the speed. So now this is the receiver's speed. And that speed is higher than the blue, but it's going to the right. So now, if I look at my velocity, it has to have the same type of thing. So I can see here that if I bring everything down, I could then just follow my picture here. The blue means what? It's going in the negative direction and it has a small speed. Then this thing jumps up all of a sudden up here. And as it jumps, you know what? I should not have drawn that like that. It's a discontinuity. So then this guy has to be like this. This is a high speed. So if I had been, I'm just coloring these to try to make sure that they're related to each other. And if I look at this here, this is the whole triangle that I'm looking at. And then finally, there's a decrease in the orange speed. So let's say right here, which will then give me a graph like this.